Okay, let's finish. So we finished chapter 1, and before I get into chapter 2, I like to quickly browse appendix A, B, C, D, but very quickly. I would not show all the slides. I would just show selected slides. And the reason why I want to go through the appendixes is because I want to arouse your interest on those appendixes. Otherwise, I'm not sure whether you would actually read them or not. So I want you to read them, and I want to show them what we have in the appendixes, and so that you would be more interested in reading them. And if you are not familiar with Linux, or not familiar with the Linux environment or the Linux development environment or the tools, then you got to read them so that you would be more handy. You will become more handy on the Linux systems. Okay. And there are 4 appendixes. The appendix A is non-technical. Appendix A is about story about who is who. However, appendix B, so appendix A, we tell you stories, and we tell you story about IETF open source community and the other community, and also some history of technologies that have failed or disappeared. There are some technologies that have been hot, that were hot in the past few years or decades, but they disappear eventually. And we in that section we talk about those history and why they failed. And appendix B, C, D are technical. Appendix B tells you about the Linux kernel. It gives you a kernel overview on the source code, kernel source tree, and the source code of networking. Remember that networking accounts for 1/5 of the kernel. So we tell you where they are, which directory, and the major functions for those networking code. And then tools for source code tracing. There's an example that you follow the example, you will know how to trace the source code with easily. You don't want to print the source code and read it on paper. You want to trace the source code with those kind of tools. And appendix C is on development tools that are for programmers, mostly for programmers. And appendix D are for network utilities that you can do some experiments. So you can explore the network environment, network configuration or packets with those tools. So these are these four appendix. And for appendix A, I want to show just the IETF. Right now, there are almost 6,000 RFCs. Well, you would wonder why we have so many RFCs. Well, why do we have so many RFCs? I think we only have less than 100 protocols in use on the internet. But how come we have almost 6,000 RFC? That's the reason. Okay. First of all, not all RFC are protocol standards. Not all RFC are describing the protocols. Probably only a little bit more than 1/3. So these 3, the proposed standard, draft standard, and standard, these 3 account for 37% of the RFC are describing the protocols. then immediately you cut into 1/3 from almost 6,000 to less than 2,000. So you have still, you got almost 2,000 RFCs describing the protocols. But again, we approximately have only have less than 100 protocols in use. So that's still a factor of 20 times, 20 times or more, 20 times or 30 times. So the reason why still almost 2,000 RFC on describing the protocol is because on the average, a protocol is defined by 20 to 30 RFCs. Why? Because, well, if you look at this table, the TCP protocol is defined by 111 RFCs so far. But how come so many? Well, these are, I show the major protocol that have more RFC defining them. The reason is because two reasons. One is usually for a protocol there's a main RFC defining that protocol, but also many other RFC defining the extensions and options. Extension and options. So you have protocol body, protocol main body defined by one RFC, but extension and option are defined by many others. That's the reason number one. Another reason will be once an RFC is written and published, it cannot be revised. It's there. However, a protocol would evolve, so you might need to add some features, some options, some extension, or some other stuff. Then you would need to come up with another set of RFC. And this new set of RFCs would obsolete the previous set. So if I have a set of RFC, say 20, defining a protocol, and because I want to have a new version, so what I do is that I would have another set, 20 RFC, a new set, and they are numbered RFC, and then they obsolete the previous set. So then by just one version update, I probably generate 20 or 30 RFCs once. And if this set of protocol RFC have been updated 3 times, then each time will be 20 more, so that'll be 60 more. So that's the reason why we got so many RFCs. Okay, is that clear? Okay, it's not like a software version that you would have 2.6.23, and then the next one will be 2.6.24, and continue. No, you don't do that. So perhaps the previous RFC is number 2027, 2627, and it could be obsolete by another RFC which is 3,528. Okay, that would obsolete the previous RFC number. So in effect, although we got almost 6,000 RFC, but a lot of them are not. 2/3 of them are not defining the protocols. They are talking about something else, and probably more than a half of them are. More than a half of the protocol defining RFC are obsolete already. Obsolete means that they have been replaced by newer RFC. So Then one question you might ask, we got about 1/3 of the RFC on defining the protocol. What are the other 2/3? The information and unclassified and historical best common practice experimental. These are just like a communicator that they probably summarize some discussion or finding as an RFC. Okay. Okay. These are some open source sites, and even the hardware design could be open source, because the hardware is actually programmed. The design of hardware is actually implemented in Verilog or VHDL code, and these are all also programs, except that they are parallel hardware program instead of sequential software program. And there's a site, website, opencodes.org, which have collect some hardware designs in either Verilog or VHDL. So you can find some network modules, say Ethernet, or some transmitter, some receiver, or some CPU, some memory control module, some arithmetic module. You can find them on this website. Actually, we draw some of the IP, some of the hardware design into this book, including crypto, and also encryption, and also the CSMACD, the Ethernet. The Ethernet controller has an open source package on this website, and we are going to describe it in chapter 3. And also some physical layer. In chapter 2, we have two physical layer modules. One is AB10B encoder, used in Ethernet and some other network modules, and also another open source implementation on OFDM. Okay, the next thing is open source packages. There are a lot of also open source packages, and these are classified. I try to classify them, and for example, here you see HTTP server. There are 97, well, perhaps more right now, 97 HTTP daemon. And one of them is Apache server. So Apache server is just one of the many HTTP servers. So the number here tell you how popular that tech category is. Okay, and what else should I show? And some history. I will skip this. So in Appendix B, we look at the kernel, Linux kernel. So perhaps it's easier to look at this figure. So there are in the kernel source tree. This is a kernel source tree. There are some kernel core on the, say, the kernel core. So, and networking here, architecture specific here. So depending on your CPU, and networking here, driver here. So most of the networking code are here and here, and under NAT, the directory. NAT and drivers. Most of the networking code are here. And here you have some, say, memory management. I think process management should be here, or here and here. And file system here. So in the layout, you will see that the networking and file system are put here. And for networking code, depending on which layer, so this page shows you the link layer networking code, and network link layer too, and then the network layer, the IP layer, and then transport layer. Okay, transport layer, and application layer is not in the kernel, so it's not listed in the table here. So you can see that at the link layer, you would have some basic receiving and sending frame will be here, and under NAT/core within this file dev.c file, you will see some function, and I just list the major function here. So these are the major functions that you would see throughout within the open source implementation of this book. Okay, so these are the most important functions, and you can find them under this directory within this file. And there's a short description on what they do. So link layer receiving and sending, and the driver PPP implementation here. And then bridging, we will, again, the link layer will be covered in chapter 3, and bridging is under the directory here. Why don't we start it from physical layer? Why we didn't? Because physical layer is hardware. However, in Linux kernel, it does not contain the hardware component. So for hardware, you need to grab from some other source like open cores, not within the Linux kernel. And then to the network layer, the basic packet forwarding, here, it's in this route.c file, and these are the major functions that you would trace within for packet forwarding. And then checksum, and fragmentation. These are smaller implementation. And then NAT, see NAT and V6, IPv6, ARP, DHCP. These are important protocols that you would need to understand how they are implemented, and also how they are designed. And ICMP, and also ICMP v6. And then into the transport layer, so you will see UDP and TCP checksum, the checksum for UDP and TCP. And also TCP sliding window flow control. And this is a big implementation within this file. And different, you will see some very complicated TCP flow control and congestion control here. And slow start congestion avoidance also in TCP retransmission. So here we break down TCP implementation into several lines, table entries here. Retransmission timer, persistent timer, and keep alive timer. FACK implementation. Okay. And then socket rewrite. circuit implementation here, the circuit implementation, and circuit filter, another circuit implementation for packet filtering or packet sniffing. So these are the kernel source code, I mean within the networking code. And within this table, all of them are covered in our open source implementations, all of them. And there are some other open source implementations like the one in the physical layer and also the ones in the application layer. They are not listed here because they are not within Linux kernel. Okay, there's an example using the tool called Lec10, which is a source code tracing tool, and actually the interface is a web interface that you can use this tool to trace any code, either whether the code is on your local disk or on a remote server. So you can use this tool under the interface of the browser to trace the source code. And you would see the source code and also who calls the source code, whether the function are referred, and who called the function, and what functions does this function call. So you will see the cross-reference. And in Appendix B, I give an example, which is a IP reassembly, and demonstrate how to use the tool to trace that piece of code. So these are IP reassembly procedure and it's a code graph here. So I will skip this example, and you can read this example to see how you might trace the source code in the future. In the future, you will trace some source code, and I don't expect you to print the program and trace the program on the paper. You should be able to trace the program with tool like this. And there are some other tool that we will see next. Lec10 is one. Okay, but some other tool, say C-scope, that we will see next. And the development tool, you will see some program editing tool. Well, you will say that I can use any editor. Why should I use a VIM or some text mode editor? Because they have fast key. They have fast key that in the program fast. So these are important fast key or command that will speed up the editing of a program. And G-editor is another tool that has a better graphic interface. Okay, and the compiler GCC, I believe that most of you have used that GCC. And I'm not sure how many of you have tried to automate the compilation process by writing the makefile. So if your compilation process is complicated, then you don't want to type in so many commands every time you try to compile your program. So what you want to do is to write the compilation process in a script file. This is a script file, which is called makefile. So you can automate the compilation process, say a series of GCC compilation, and also So you will see those. Well, it's just a simple example of a makefile. Usually, the makefile will be a meaningful job. A meaningful job would require a makefile, and you put everything. Every steps of the compilation into the makefile. Okay. Another tool is debugging tool, GDB and KGDB, and I know many of you use printf to debug, but printf is sometimes if you for a small program it's okay, but for a large program it might not be enough. Okay, to use a printf or printk. Printk is used when you print something in the kernel. When your program is in the kernel, you want to debug your program in the kernel, or show something within the kernel. So then you write printk. But these printf and printk are not enough. If your program is large, then you will need to rely on debugging tool like GDB and KGDB. GDB and KGDB, one is for user space program. If this is user space program, then you use GDB. But if it is kernel space program, you would need to use KGDB. KGDB. And we describe them in the text. And both of them would allow step-by-step source level debugging. Step-by-step source level debugging. So you can stop anytime, at a step, and then print out some variable to check the value to see what went wrong. And DDD is a graphic user interface debugging tool. So it provides you a better graphic user interface, but the idea is the same. Okay, and we mentioned LXR, which is a source code tracing tool, and another tool will be cscope, and it will give you again the cross reference of the program. Who calls whom, and also searching. Okay, another tool is Git. Git is a version control, distributed version control tool. Now it's getting so popular that many major projects use them, including in Linux kernel itself. The Linux kernel development is managed by Git, and also Android. The Android development is also managed by Git. And before Git got so popular, the previous tool are CVS and SVN. CVS stands for concurrent version control, and SVN stands for subversion. So they are again for a group of programmers, a group of developers. They want to write code at the same time, and they might commit. They might update the same piece of code. Then you need to do pretty good version control, and also conflict resolution, so that multiple developers can work on the same project. So these are the purpose of this kind of tool. And Git is becoming more popular than CVS and SVN. They all do the same thing. Profiling tool, gprob and kernprob. Gprob and kernprob. Kernprob, not shown here, but in a book. That you want to, you see that we profile the time spent on different layers and functions, and that's done by kernprob and some other tools. Kernprobe has been used. gprobe is like GDB and KGDB, one for user space, one for kernel space debugging. gprobe is for user space program profiling, and Kernprobe is for kernel space program profiling. And by profiling, we mean that we want to know how much time a function spent or consume the CPU time. The CPU time consumed by the function. So then you would see the bottleneck. So this is to identify the bottleneck within the program to see which function will be the bottleneck. So they can measure the CPU time consumed by different functions. Okay, BusyBox is an embedding tool, embedded system tool that when you are preparing an embedded system image, meaning that you want to create an image that contains everything, containing the file system, the kernel, and the application program within the image. And usually, you don't want your image to be too big. You don't want your image to be as big as a Linux distribution. Usually, a Linux distribution will be several gigabytes, right? But if you want to put it into a tiny machine, say in a handheld device, then you want to create an image for your cellular phone, for example. Then the image size should be limited to several megabytes instead of several gigabytes. So you need to be careful about what you put into the image. The file system, the kernel, and application, and the log space, those need to be calculated, need to be downsized. And BusyBox is a set of utility tools that you can, that they are small and very suitable to be included in embedded system image. So when you are building the image and you need some tools, you don't want to grab the giant tool, the big tools. You want to grab the small tool. Say, I want to put a web server in my, say, my access point. I have a wireless access point product. I want to put a web server because I want to do web-based management on this AP. So I need to put a tiny web server. Should I put Apache server in this image? No, Apache server is too big. They are smaller, very small web server, and they are within the BusyBox. I can grab those kind of tiny server into my image from BusyBox. Okay, so if you need to, it's like a Swiss knife. It got everything, and everything there is small, very suitable for embedded systems. And how about make the image? Do you need a tool? Yes. Do we have a tool that can help you to build the image containing file system, kernel, applications? Yes, we do. And library and log space. These are to be contained in the image space. And build root is such tool that you build the root image for the embedded system. Okay. Okay, so that finished Appendix C for developers. And next is Appendix D is on network utilities. Many small tools that you can help you to explore the internet. Okay, host, the command, the tool host is to map between domain name and IP address. So with domain name, you can say host Google. You will see that where the Google machines are, or some of the Google machines. And ARP is host is but translation between domain name and IP address, and vice versa. You can translate from IP address to domain name. Okay, the reverse translation. And up is translation between IP address and the MAC address, the NIC card address, and also the IP address, and vice versa. That's up, ARP, Address Resolution Protocol. And IFConf is to know who I am, what I have. Okay, to know this machine, to see you see the IP address and MAC address, the hardware address, and something else. So that's IFConf. You check your own configuration. Okay, ping is a tool to probe the internet. To probe the target machine. You want to probe the target machine to see if it's still alive. And the response time, the round trip time from me to that target machine, then you use ping. If you want to know the path between yourself to that machine, or between machine X and Y, then you can use trace path or trace route. Okay. And actually, they use we talk about in this how it's implemented in chapter 4 in the IP layer. Okay. But now you just need to use it. And with this, you can find interesting stuff, like you want to see from here to some particular machine, what is the path? Within this path, what are the routers? So you see the router, totally 14 routers in the middle, and you will see the delay in each hop. So you will see the delay in millisecond scale. Okay, and then you immediately see that it's the bottleneck. It accounts for 44 milliseconds, 23 milliseconds. So you will see which link will account for more delay in the path. That's trace path. TCP dump or Wireshark. TCP dump and Wireshark are used to sniff packets. You want to listen to packets and pass the packet and see the packet, and you use TCP dump or Wireshark. So you would be able to decode the packet. See, each line here is a packet, and then it would decode the headers and show you the binary, well, in hexadecimal. Okay, next stage is to show you the connections on this machine. Show you connection on this machine, and also show you the routing table. It will show you a connection on this machine and routing table on this machine. TCP is a tool, benchmarking tool to test a device, to test the throughput, TCP throughput. So you will pump a lot of packets to measure the throughput. So it's a benchmarking tool. NS and NIST, NET is one is the simulator. It's a simulator, network simulator. It could simulate a network or simulate a protocol. So I can simulate wireless LAN, CSMA CA with the NS, or I can simulate a network topology. So that's NS, and it's commonly used by many people. And NIST is an emulator. Simulator and emulator are different. Emulator is actually the time is spent on processing really depends on that machine. It's emulation instead of simulation. And here the NIST net can simulate packet delay, loss, and jitter. So say I want to, between this, say these two endpoints, they have traffic, and I want to simulate they have 10% packet loss. I can configure here a NIST net to configure 10% packet loss. or I can configure the latency is mean latency is 10 milliseconds with some distribution, and also the jitter has some distribution. I can configure that on this emulator. Okay, Nexus is a hacking tool that would try to find the vulnerability of a target machine. You can try to find the vulnerability of a target machine. So it's a hacking tool. Okay. So I quickly browse the appendix A, B, C, D in the hope that you would know what resources or what material we have there, and browse them, try some tools. Okay,